can't hurt us. Now, elements in the body. These are elements that are making us up. Now, granted, some of these elements more in composition than others. Some of them we only need in trace amounts. Others that are not on this list is the stuff that we're getting exposed to every day, through the air, through the water, through the food, okay? And the body's trying to have to determine what to do with it, okay? But we know that carbon, hydrogen, nitrogen, oxygen, biggies, okay? That's what's making up a huge amount of us. Other ones are existing in trace amounts or very, very small amounts. However, when we begin to look at fluorine, sodium, magnesium, phosphorus, sulfur, calcium, some of these, potassium, calcium, okay, those, guess which side of the periodic table they're found on? They are found under my metals. Now, well, fluorine and chlorine, okay, are found under my gases. Does everybody follow me? Okay. Iron is going to be here as one of my transitional metals. Okay, as well as the iodine. Why do you think that information is important? Well, guess what? It is. Now, think about this for a second. Of those elements that were listed, what were some of the biggies? Forget the CHON right now. Let's look at our ones that are like the fluorine, chlorine, potassium, nitrogen, stuff like that. All right. So what were some of the biggies? Forget that one right now. Potassium, magnesium, our chlorine. How about the sodium? All right. Guess which two, from this point forward, you will hear every single day, especially from me. Sodium, potassium, and we'll go ahead and add chlorine because that's true. Sodium, potassium, chlorine. Now let me think about this for a second. When you look over here under the heavy metals, okay, sodium, number 11, so that means we kind of go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to usually fall about right there on the periodic table. Sodium 11, running out of room, with roughly a mass of about 22, 23. Okay, somebody tell me if I'm wrong. Is it in one of the pictures on the book? Do y'all have the book up or the notes? Notes. All right. I want to see 20. I want to say 23. 23. Okay. Sodium. The only way you can keep it under lab conditions is to put it in a very heavy oil, because the minute air touches it, it blows up. Hey, I paid $10 to see that. You know, from what I can understand, in World War II, they would drop blocks of sodium into bodies of water because they would blow up. Like, cool. Okay? Now, chlorine. Chlorine. Clorox. Ever been around that?
Clorox wipes.
Like the Clorox in the gallon jug. And you open a jug and it's like, woo. Okay? It's actually a very deadly gas. It was used in the gas chambers by the Nazis. But wait a minute. I got this really nasty gas, deadly, this really reactive metal that can be deadly. But wait a minute. I put them together and I get something called sodium chloride, which a lot of times makes me think about what? Table salt. Which table salt is a mixture of like potassium, magnesium, all the other ones too. And depending on what type you buy, might contain iron. All right? But you got to check for that iodized portion, okay? Which they don't really have a whole lot of anymore. That's a whole other story. Okay, so sodium chlorine. And I think chlorine on the periodic table is number 17. Somebody check it for me. With a weight of 35. Check it for me.
There's a project here last week that can put on.
I can't read that. 17 with what for the weight of?
17.
Oh, I was right. Woohoo! Score. Okay, so now I got to figure out between these two atoms that, trust me, from this point forward is going to become your favorite atom to talk about, your favorite molecule to talk about. Why is it so special?
That works along with the actin and myosin in your body, the sodium and potassium.
It's going to be with everything. When I say everything, I mean everything. Okay? But why? Let's think about this for a second. Okay? All right. Mention that sodium, number 11, chlorine, number 17. If I were to look at my structure, I know I've got my nucleus, right? I don't have much board space, and I just don't know how to get this into the camera yet. We got to figure out the logistics of that. Let's say we're looking at sodium, number 11. My first has 2 electrons. The second one has 8. How many of my electrons have I used? 8 plus 2, 10, and I have 11, right? So that tells me out here in this great big third shell that could hold up to how many? 8 or 18. That's huge, okay? There's only one. This is my sodium. I mentioned that sodium, very highly reactive. So reactive, if air touches it, blows up. This is why. Because that one little itty bitty, which is not really itty bitty, but it's itty bitty, okay? Electron out here is not happy at all. I mean, it is the most unhappiest electron that you can probably find. other than on some of the other metals, just saying. Now, chlorine. My nucleus, 2, 8, goes into my third shell. How many do I have left in my third shell? I got 7. Third shell can hold what? 8 or 18. So now I'm looking at a situation where I've got 7 in this outer shell. How many does it need to become happy? Ta-da! Chlorine meets sodium. Sodium meets chlorine. You have 1 electron. You have 7. Oh, we're just meant to be. Okay? So now, chlorine goes, yes, come here. And sodium goes, bye. Lets that 1 electron go and sends it over here to chlorine, whoops, plus 1. I now have 8 electrons. Sodium's happy, chlorine's happy. But wait a minute. Somebody gave up the electron, somebody accepted the electron. That means something changed. Okay? So, when this happened, where I should have 11 protons, 11 electrons, I now have 11 protons, 10 electrons. So now, what's stronger, the positive or the negative? Protons are 11, electrons are 10. So what's stronger? My positive. This now takes on a positive charge. Down here, I have 17 protons, 18 electrons. What's stronger, the positive or the negative? Our negative. When we change that electron number and someone gives up the electron, the other one accepts it, we have given them a charge. They are now a charged particle. These are known as an ion. We'll have one that's positively charged, one that's negatively charged. Now, when we talk about bonds between the elements, bond strength changes. Some of the bonds are very strong, some not quite, some are weak, okay? When we talk about the bonds that exist, we can have covalent bonding, we can have ionic bonding, and a couple of different ones exist. When we do the ionic bonding, such as what you see right here, the bonds are mid-strength, but they're also weak. How can that be the case? Because when you take something that is held together with ionic bonds, lots of chlorines, lots of sodiums. Think about a piece of salt, all right? Think about just that one little piece, okay? You put it in water.